All right, so we're going to talk about spectral lines. We'll have more to say about the details later, but we'll just remind you, because you have to do it 13 times, of the Bohr model. So in other words, of course, the Bohr model doesn't deserve to work, but it does very well for hydrogen. It really doesn't, you know? And as I've said before, I would be a smarter person if I really understood why the Bohr model ends up working. As in, why does it give the same results as the Schrodinger equation for hydrogen? Why? Okay, but it does. It's a miracle. I mean, it's not, it's math, but how does that happen? It's a miracle. It feels like a miracle to me. And if I were smart enough, maybe it wouldn't feel like a miracle. I would just know, well, no, of course, it's because, but I can do the math, but at the end it always just looks like, oh my God, it's a miracle. So, anyway, let's talk about the rules first, kind of take the historic approach. The so-called Kirchhoff's laws were worked out before we understood what was going on. So here's the rules. That there's three kinds of spectra. You've got a continuous spectrum, which is, for the visible part of the spectrum, a continuous rainbow of color. Every wavelength is present. And so you get a continuous spectrum from a hot, dense light source. So for example, the light bulb filament is the classic example. But if you heat up a liquid to a high enough temperature for it to glow, it will give off a continuous spectrum. Even a dense gas will give off a continuous spectrum. So one of Kirchhoff's three laws is that a hot, dense substance gives off a continuous spectrum, as illustrated on the top. In particular, ideally, it would give off a Planck spectrum, thermal radiation described by a black body spectrum. On the other hand, if you have a hot cloud of gas, such as when you plug in a hydrogen vapor lamp or mercury vapor lamp or whatever, then what we find is that you get an emission line spectrum, so in other words, specific wavelengths of light being given off, and light of no other wavelength being given off. And so that's illustrated there with a hot cloud of gas, pass the light through a slit, spread the light out into its colors with either a prism or a diffraction grating. You get a bunch of images of the slit, which we call spectral lines. Specific wavelengths of light put out by each gas that serve as a sort of spectral fingerprint. So that's the second type of spectrum you can get. The third kind, the absorption line spectrum, is where you have a continuous spectrum that is crisscrossed by dark lines where light is missing. And you get a continuous spectrum by taking a cool cloud of gas and putting it between you and a hot light source. Pass the light through a prism or a diffraction grating, spread it out into its component colors, which again, you're really just seeing a bunch of images of the slit. Well, the cold cloud of gas, where cold really means cooler than the hot light source is, will absorb light of specific wavelengths. In fact, the same wavelengths that it will emit if it's a hot cloud of gas. And so you have light missing from the spectrum of those wavelengths, and so you get a bunch of dark absorption lines. So Kirchhoff worked out those, or he enunciated those rules before anybody understood what was going on. Now, we know what's going on, so we'll talk about that. But in any case, pointing out again, every chemical element has its own unique set of spectral lines. And that's the key to knowing what things are made of. We can look for spectral lines in distant astronomical objects, and by comparing them with the known wavelengths of spectral lines on Earth, we can figure out what different celestial bodies are made of. So there's illustrations of hydrogen spectrum, sodium spectrum, helium spectrum, neon spectrum, mercury spectrum. Every element has a spectrum, molecules have spectra, everything's got a spectrum. Set of spectral lines that will uniquely characterize it for each element, and even each ionization stage of an element. Doubly ionized calcium has a different spectrum than singly ionized calcium has a different spectrum than neutral calcium does, for example. As I mentioned, spectral lines of an element are always at the same wavelengths for both emission and absorption. So if a given species of atom emits a certain set of spectral line wavelengths, it also absorbs exactly those same spectral line wavelengths. Here's the sun spectrum, spread out, snipped up and stacked. It's a lovely rainbow crisscrossed by literally millions of dark spectral lines called the Fraunhofer lines, after Joseph Fraunhofer, who first saw them. So lots and lots of absorption lines in the sun spectrum, and by matching up the wavelengths of spectral lines in the sun spectrum with laboratory spectra, we can figure out what the sun is made of. And the answer is it's made of every imaginable element, turns out. So anyway, this is an example of doing it for iron. On the bottom is an emission line spectrum of iron. So you vaporize iron, heat it up to glow, get an emission line spectrum. You can match it up with absorption lines in the sun spectrum and say, aha, the sun contains gaseous iron, and gaseous praseodymium, and gaseous yttrium, and gaseous everything else. But it's mostly made of two elements. Do you know which ones? Overwhelmingly, the sun, like all normal stars, is made of hydrogen and helium. Yeah, by far, mostly hydrogen and helium. In a later chapter, we will talk about how that was determined by Cecilia Payne when she did her PhD thesis. Good Lord, making a PhD thesis where you determine that most of the ordinary matter in the universe is hydrogen and helium. That's a pretty good accomplishment for a grad student. So, the quantum mechanical understanding of matter, well, of course, you know, this is a figure from an intro astronomy textbook. In 280 we did, or you did more detail. In 380 you do a lot more detail. But remember that, of course, electrons don't literally orbit the nucleus in well-defined orbits the way planets orbit the sun. In fact, we describe them with a quantum mechanical wave function that describes the probability density for finding the electron in various locations around the nucleus. And so we talk about an electron cloud because the electrons act like they're spread out in space around the nucleus. So the classic model of, you know, helium with two electrons nicely orbiting, of course, is just a convenient BS fiction. And in reality, it's much more complicated than that. It is true, however, that protons are little red balls and neutrons are little red balls. With that, that's true. Okay. Glad that you're laughing. If you weren't laughing, I'd be like, oh, good God. So, and of course you know that unlike, say, you know, if you use an analogy between gravitational potential energy and electrical potential energy, if you have if I had a plank, a wooden plank, I could imagine as I get different heights above the floor, I have different amounts of gravitational potential energy. If I walked a plank between the floor and the tabletop, I could be anywhere along the plank, so I could have any amount of energy. But the way, because of quantum mechanics, that electrons in an atom behave, in fact, they're only allowed to have certain amounts of energy. So the nice analogy here is like a bookshelf. They have the book on certain shelves, no in between shelves, and so the book is only allowed certain amounts of potential energy, nowhere in between. Of course, in reality, you can move the book in between, but in quantum mechanics, like, no, it really isn't in between, or strictly speaking, the electron's wave function can be a superposition of states, but it can never be anything in between. It can be a quantum superposition of different energy levels, but never literally some energy in between those allowed energy levels. And so we use energy level diagrams to illustrate the allowed states of the atom. So you've got a ground state, which is the lowest possible energy by analogy with gravitation, where I can't lower my energy below what it is on the ground. That's why it's called the ground state. And then you've got all these excited levels that the electron can be in. And so, of course, quantum mechanically, it can have different orbitals for the electron. And collisions can give the electron the energy it needs to move up from the ground state to some higher energy orbital in a hydrogen atom. But so can photons. It can absorb photons in order to do that. But of course, the rule is that the photon has to have exactly the energy difference between two allowed energy states in the atom. Nothing in between is allowed. In fact, because of the energy time uncertainty principle, there is a narrow intrinsic width for the spectral line. You actually have a very narrow range of energies that can cause the transition because the energies actually aren't perfectly well defined, but they're quite sharply defined. And so to a rough approximation, you can say, pretty good approximation, I should say, photon has to have exactly the right amount of energy in order to cause the transition. It could be to infinite precision because then nothing would ever happen because you're not going to have the right energy to 66 quadrillion, zillion, billion places after the decimal point. It could be as ridiculous as that. There'd be no transitions in that case. But the photons themselves don't have perfectly well-defined energies. The energy levels themselves aren't perfectly well-defined. So there's a little wiggle room, but you need almost exactly a certain amount of energy to cause a transition between two allowed energy levels in the atom. So here's a simple model of a two-level atom, and the only photon energies that it can give off corresponds to the energy of the transition from its upper level down to its lower level. It can't give off any other wavelength. And furthermore, that's also the only wavelength that can absorb. The reason why the spectral lines are the same wavelengths in both emission and absorption is the difference between moving up and moving down. Whether you are jumping from a higher level to a lower level and spitting out energy, or jumping from a lower level to a higher level and absorbing that same amount of energy. So here's our two-level atom having a photon come in whose energy is equal to the difference in energy E2 minus E1, causing an upwards transition. So our simple two-level atom would both emit and absorb that same wavelength. In a real atom which has multiple energy levels, there's a certain set of energies that can emit and absorb corresponding to the different transitions, different energies that allow transitions between the levels. And the idea then is if I heat up a gas containing our two-level atom, collisions would bump some of the electrons up to the higher energy level, and so that gas would emit that wavelength when electrons spontaneously jump down to the ground state. And similarly, if I have a source of continuous spectrum, every wavelength is being emitted, and then I have a gas of those atoms in front of it, then the photons that have the right energy to cause the transition can be absorbed by those atoms and then spat out in other random directions so that they are removed from the beam. And so then the beam itself is missing light of the wavelength that the atoms can absorb, and so you get an absorption line, a line where there's a wavelength where there's light missing, and all the other wavelengths make it through. The gas is transparent to those wavelengths because those wavelengths aren't the right energy to cause any transitions in those atoms. And if you have a more complicated situation where there's lots of atoms with lots of possible transitions, then you get light missing at wavelengths where transitions can happen, and other wavelengths the gas is transparent, and so you get a lovely absorption line spectrum like that. So that's how it works in a nutshell. Any questions? All right. So I will assume there's no questions because it's all clear, been there, done that. Is that a reasonable approximation? All right. So let's be more specific now. So I'll leave this up, but let's remind ourselves of how the Bohr atom works. And the miracle that quantum mechanics Schrodinger equation gives the same result if you leave out electron spin, orbit coupling, and all that kind of stuff. So let me get the lights up here so I can start writing on the board. My eyes, it burns, it burns. Didn't what?
We didn't acknowledge Diego today.
Diego today. Hi, Diego.
You're dead to us.
Oh, that's sad.
You know what you need.
I want to see if this is pointing at, yeah, let's see. Yeah, yeah, good enough. Here we go.
You probably close this before we do that class. But not before. I didn't know. Like I could sprint over. You could, theoretically, in the break, sprint to there. Pick up something and come back. I know that the Hamlet Cafe closes around 4:30. I would assume they're closed.
Hydrogen is so important, and even though you've seen this before, it's still worth going over again. The Bohr model of the hydrogen atom. So, Swiss school teacher Johann Balmer found an empirical formula for the wavelengths of the spectral lines of hydrogen in 1885 for the visible wavelengths. Empirical formula for the wavelengths of the visible hydrogen spectral lines. Look like this. The reciprocal of the wavelength, 1 over lambda, is a constant r sub h that we call the Rydberg constant, times 1 over 4 minus 1 over n squared. So n is an integer, and r sub h, and it's an integer that is greater than or equal to 3. And r sub h is equal to 109,677.585 plus or minus 0.008 inverse centimeters. We'll just stick with CGS here. Called the Rydberg constant. So that's what Balmer found for the visible spectral lines, but 4 is 2 squared, so this suggests that maybe this generalizes, and of course it does. Since 4 is equal to 2 squared, this formula naturally generalizes. To 1 over lambda is equal to the Rydberg constant times 1 over m squared minus 1 over n squared. 1 over Mary squared minus 1 over Nancy squared. And then tell apart and say m. So m and n are integers. With positive there, so I want m to be smaller than n, right? Because then 1 over n squared is bigger. Yeah. With m less than n. And so what you get is a whole series of spectral lines for each of the different values of m that you can pick. So if m is equal to 1, that gives us what we call the Lyman series. And if m is equal to 2, that's the one we call the Balmer series. M equals 3 is the Paschen series. M equals 4 is the Brackett series. Because basically, there was a time where everything, the low-hanging fruit was still there for the picking, and so you could just get a series named after yourself. M equals 5 is the Pfund series. Once I had a student named Kirsten Pfund, and she rather liked that we had Pfund series in there as well. And so, there's an infinite number of m values, so you can just pick some large one and call it your series. Nobody's stopping you. So, no one will recognize it either, but, it's kind of like the International Star Registry, Just pick some dim star and name it after you and put it in a book that gets filed with the Library of Congress. Like every book! And then sell that to people. Anyway. So, as we know, so we would have this problem classically. So if you make this model where you have an electron orbiting a proton, like a planet, that would not work, classically speaking, because accelerating charges radiate. If a charge is accelerating, it's radiating. So, classical model of an electron orbiting the nucleus like a planet won't work. Because in classical E&M, classical electromagnetic theory, accelerating charges radiate. We haven't showed that, but it works out to be true. Solve Maxwell's equations for an accelerating charge, you will produce electromagnetic radiation as the result of that. So, if I had a proton orbited by an electron, maybe some nice circular orbit, you make an ellipse too if you wanted, is that thing accelerating? Is the electron accelerating if it's going around the nucleus on a circle?
Well, yes, because it's changing direction.
It's changing direction, right? Yes, not speeding up or slowing down, but it's changing direction. Uniform circular motion is accelerated motion, right? The electrical attraction could be what's providing the force on it to get it to not move in a straight line. So the electron should continuously radiate and lose energy. continuously radiate away its orbital energy. And if you run the numbers, you find it should spiral into the nucleus in about 10 to the minus 12 seconds, about a trillionth of a second. Observationally, atoms have existed for longer than a trillionth of a second.
Wow.
Yes, from this we conclude that this doesn't actually happen.
That just isn't proof.
Yeah, he's a proof.
I don't believe
He
it.
said in a time which was long enough to illustrate the fact.
Were you there? Did you see that?
Yeah.
Did you see the kids?
Right. Calculations show the E minus should spiral into the nucleus in about 10 to the minus 12 seconds. The universe is somewhat older than this. Conclusion, this does not happen. I know it's profound, unexpected, but yeah, we can conclude this doesn't happen from the fact that I'm talking.
Just all of a sudden it just
Yeah.
stops. It just
All of a sudden, that's right, yes. So Bohr came up with a solution, which was very ad hoc. He just said, well, let's just suppose that the electron is only allowed to have certain amounts of orbital angular momentum. Of course, now we understand that quantum mechanically, but Bohr was just like, I'm just going to make something up and see what happens. And miraculously, he gave the right numbers for hydrogen. That worked for anything else, but it works for hydrogen.
It's kind of strange.
Yeah.
There's 26 dimensions.
Yeah, I counted. There's only 23.
There's only 20.
Yeah.
Were you there?
Yeah.
Well, the fourth dimension says that was
So in 1913, Niels Bohr, Danish physicist extraordinaire, proposed that the angular momentum is quantized. Okay. That orbital angular momentum of the atom is quantized. Only allowed to have certain specific values, is what, of course, we mean by quantized. According to L is equal to n h bar. H bar being the reduced Planck's constant. Sometimes h bar itself is called Planck's constant. That may be a better name for it if we reserve h for Planck's constant. That's the reduced Planck's constant, h over 2 pi. No other values allowed.
None in this tree.
What's that?
So not in this tree house.
No, none in this treehouse. And this allowed him to construct a semi-classical model of the atom. Semi-classical simple model of the hydrogen atom. We'll do it upright here. We'll use the reduced mass. You should use the reduced mass rather than the mass of the electron. Since we know about reduced mass, we'll go ahead and put that in. So, if I have charges Q1 and Q2, and they are distance r apart, we know Coulomb's law says that the force is, we'll call it K sub c because that's what your book does, Coulomb's constant K sub c times Q1, Q2 over r squared is the force. And of course, Coulomb's constant is 1 over 4 pi epsilon naught. And you've certainly memorized by now that that's 8.988 times 10 to the 9th power Newton meter squared or Coulomb squared. Actually, I haven't memorized that. Almost 9 times 10 to the 9th Newton meter squared Coulomb squared. So, for our model, of course, what we've got is the proton and the electron exerting an attractive force on one another. And charge on a proton is plus E, charge on an electron is minus E, where that number E is not the base of the natural logarithm, of course. It's 1.602 times 10 to the minus 19 coulombs. So we've got two charges, plus E and minus E, exerting forces on one another. So Q1, Q2 is going to be in magnitude E squared, charge on an electron squared. And I never changed my notes for this, so I think I'll just, it's fine. I'll just keep some nasty 4 pi epsilon. No, I don't want to do this. I can just keep K in there. So what am I doing? What are you doing, DH? Yeah. We'll use CGS units because then K is 1 in CGS units. If it does, okay? So worth seeing at some point how nice CGS units can be. In CGS units, we define the Coulomb constant to actually be equal to 1 in CGS units. So F would be just, in the generic case, Q1, Q2 over R squared. Notice that changes the charge units compared to SI, because you no longer have that constant out front multiplying the charges over R squared. So the force force on two charges, each of magnitude 1 ESU. So you call the charge units in CGS ESU, electrostatic units. That are 1 centimeter apart. Is 1 dyne. In CGS units, the force unit is the dyne. So in SI units, of course, the force unit is the, what do we measure forces in?
Newton.
Newtons, right? And a Newton in terms of fundamental meters, kilogram, second units is what? A Newton is one, what?
Kilogram per second squared.
Yeah, kilogram meters per second squared, right? Mass times acceleration. So in CGS units, we do the same thing for the dyne. So instead of a kilogram meter per second squared, it's going to be a CGS, centimeters grams second. So it's going to be a grams centimeters per second squared. Yep, is 1 gram centimeter per second squared. So that's going to be 10 to the minus 5 newtons, because a gram is 1,000th of a kilogram, a centimeter is 100th of a meter, seconds are the same. So this is 1/100,000th of a newton is 1 dyne. In terms of energy, so we have what's called the erg. So an erg, well, what's a joule in terms of kilograms, meters, and second? A newton is a kilogram meter per second squared. A joule is it's a newton meter, right? Or in other words, a kilogram meter squared per second squared, right? So 1 joule is 1 kilogram meter per second squared. By analogy, 1 erg is 1 gram centimeter squared per second squared. So since I've got another centimeter instead of a meter, it's another factor of 1/100th, and erg is 1/10,000,000th of a joule. So in CGS units, forces are dynes, each of which is 100,000th of a newton. Energy is ergs, each of which is a 10,000,000th of a joule. And charge is defined in ESU such that two charges that are 1 ESU apart, that's 1 centimeter apart, exert 1 dyne of force on one another. So the charge unit in CGS is ESU defined in that way.
I feel like all of CGS units are just complicated ways to make things one.
Yes, well, no,
Astronomical
if you
units.
think about it, no, CGS units are better actually in many ways than SI units are. We could have made SI units just as good, but we didn't. SI units are engineering units. CGS units are more like theoretical physics units because there's no reason why that you have to be multiplying by 1/4 pi epsilon naught, right? Epsilon naught is the weird thing. Why bother to put 1/4 pi epsilon naught in your expression for Coulomb's law? Why not just say it's the product of the charges divided by the distance squared as the force between? Isn't that easier? So really, it's the SI units that's finding complicated ways to make things that should be 1 not equal to 1. It's really the other way around. Yes?
It's kind of like a hypothetical question. If we did start off using CGS units, how would we know what epsilon naught is?
Well, epsilon naught is this artificial thing. In CGS units, there's no such thing. If you called it if you were going to call it something, you would just, basically, there's no reason to even define it. So, in SI units, when we talk about capacitors, right, we have epsilon for capacitors. And the relative permittivity is the ratio of epsilon to epsilon naught. In CGS units, there's no such thing as epsilon naught, and there's no distinction between relative permittivity and epsilon. They're just the same thing. So in other words, the dielectric constant is the same thing as the relative permittivity. Because another way to put it is, you put a dielectric in there, and it tells you how many times bigger is the voltage compared to if you just had a vacuum in there. So, and so that's epsilon versus epsilon naught, and that ratio is the relative permittivity. In CGS units, you don't even bother with this, whatever the hell this epsilon naught thing is. And you just say that the dielectric constant is epsilon, and it's the rate. You don't even have to talk about relative permittivity because the permittivity, quote unquote, of the vacuum is 1, because there's no real reason to talk about the permittivity of the vacuum. It's a completely artificial construct that came about by accident because the units were set up before people really knew what was going on, is what it comes down to. So there's no reason for there to be an epsilon naught in the first place. It's a completely artificial construction. Why talk about the permittivity of the vacuum? Why not just make it 1, So really it's, I see what you're coming from, but really what it comes down to is it's the SI units that are artificial. They are complicated ways to make things that should be 1 not equal to 1, forcing them not to be 1. So, believe it or not. And in fact, in the first edition of our textbook, they use CGS units because those are really theoreticians' units. But enough people complain that students don't come in with intuition for CGS units that they switch to SI units. And SI units do make more sense for engineering in that the numbers you get in SI units are often kind of more reasonable numbers than you get in CGS units. But if you're doing theoretical calculations, SI units just get in the way. It's better to use CGS units. And even better to use natural units for things like C is equal to 1 and stuff like that. Usually we call it natural units. C is equal to 1, G is equal to 1. You can make a unit system where fundamental constants are all equal to 1. And really that's what we should be doing. Nature, there's no reason not to do that, other than they give you funny numbers if you're doing actual practical computations. But from a theoretical standpoint, better to do it that way. Okay, so in Bohr's planetary model, we have to really realize that both the proton and the electron would be moving. They'd both be orbiting their center of mass, right? It can't be, just like it can't be that the sun is sitting, if you had the sun and the earth, it can't be that the sun's sitting there and the earth moving around a stationary sun. That would violate Newton's laws of motion because the earth pulls just as hard on the sun as the sun pulls on earth. The sun's a lot more massive, but it still has to move. And so both earth and the sun revolve around their common center of mass if you had just the Earth-Sun system. It would have to be true for the hydrogen atom as well. Both the proton and the electron would be making circles around the common center of mass of the system. In other words, we should describe everything in terms of reduced mass rather than the mass of the electron to make it more accurate. And you do see that. You can see spectroscopically the difference between what you would calculate using the reduced mass versus the mass of the electron. And the reduced mass is the one that gives you the right numbers. So, in Bohr's planetary model, we call it planetary because we do think of it as being an analogy to a planetary, like a planet going around a star kind of thing. In Bohr's planetary model of the H atom, We replace the electron of mass me and proton of mass mp orbiting their mutual center of mass with a particle of reduced mass mu equals me mp plus mp, blah, 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 blah. So we'll write all that out. We replace the electron of mass m sub e and proton of mass m sub p orbiting their mutual center of mass with a particle of reduced mass mu. So as usual, the reduced mass is the product of the masses divided by the sum of the masses. So mu will be me mp over me plus mp. Well, the mass of the proton is about 1,836 times the mass of the electron. So you'd be looking at mass of the electron times about 1,836 times that. Not exact, I'm just roughing it there. Over mass of the electron plus 1,836 times the mass of the electron. So in other words, you get 1836 on the top and 1837 on the bottom, essentially. In other words, this is going to be much closer to the mass of the electron than it is to the proton. And if you put in the exact numbers, you get 0.9994556 times the mass of the electron. But again, that's enough to make a difference in where you would see the wavelengths of the spectral lines. It does show up in the energies. And spectroscopy shows that it's the reduced mass that gives you the right answers. It also says that if you have something like deuterium, which has an extra neutron in the nucleus, it's heavy hydrogen, its spectral lines are at a slightly different wavelength because it's got a different reduced mass, because the nucleus has become more massive. So you can tell apart hydrogen and deuterium, ordinary hydrogen and deuterium, you can tell them apart spectroscopically. They're very similar, but there's slight shifts in the spectral lines for deuterium because the nucleus is a bit more massive than deuterium. Twice as massive, but in other words, it slightly changes the reduced mass. So that particle of reduced mass is orbiting a fixed center of force, just like remember that the bigger mass, that the system mass is kind of nailed in place in space-time with magical space-time nails, orbiting a fixed center of force. Only this isn't gravity, so it's the electrical force between them, not the gravitational force between them that we're interested in. So, what we can think of is you can imagine, although it really doesn't matter which one you have to consider, it doesn't really matter which one you call the one kind of nailed to the origin, but since the reduced mass is very nearly the mass of the electron, we typically think of the reduced mass as being a negatively charged particle orbiting a positively charged particle that's fixed in place. But you get the same numbers if you reverse that. It's really not intrinsically that the reduced mass is the negative one. So there's a plus particle, there's a minus particle. We think of that one as being the reduced mass orbiting a fixed positive charge. Sigh. All right, I can fix that. You're smart enough to draw it the right way first. What?
I forgot my eraser today.
You forgot your eraser today, and now
I
you
have
got
trouble
it.
erasing things.
All you have to do is just totally scratch it out and then just start over again. It'll be fine. It's fine. So there's the radius of the orbit, and then we can say that we will, and as soon as we're done, we'll take a break, equating the centripetal force with the electric force. Well, it's not really equating the two, I should really say. That's the centripetal force is the electrical force.
How are you guys?
Be sure to write it upside down. So, E squared over R squared, in CGS units, the force is just Q1, Q2 over R squared, so E squared over R squared in magnitude, because both charges are charge E plus E and minus E. E squared over R squared is equal to mu v squared over R, right? Because the centripetal force is mv squared over R. In this case, it's mu v squared over R since it's the reduced mass. So E squared over R squared is mu v squared over R, says that the electrical force of attraction is providing the mass times centripetal acceleration, the force that's causing the acceleration. And so the MA, in other words, is mu v squared over R for uniform circular motion. So you don't look half an hour for stuff.
I'm just trying to figure out how the reduced mass made it though.
Because remember that we can pretend that we've got a fixed force center orbited by the reduced mass. And so,
That's the centripetal.
yeah, and so the centripetal force on the reduced mass is mu v squared over R. Yeah. mv squared over R, but this is mu, so it's mu v squared over R, equals the electrical attraction force E squared over R squared. And we'll go from there after the break.
Did you guys put your homework on
Oh, we didn't.
Oh yeah, there's the homework,
there? I didn't see you guys.